Uh, hey guys, I'm here to present on Fermat theorem, which is it's a theorem that has a formula that is used to easily get the least residue. As you can see, the formula used is a to the power of p minus 1 is congruent to 1 modulo p, where p is a prime number, a is not equal to 0, and a is not a multiple of p. That is, those are the conditions that need to be met to be able to use Fermat's theory's formula. Okay, now let's say that you want to get the least residue of a number 18 power 18. Now with the traditional method, to the modulo of 7, now with the traditional method, you'd have to simplify and break down this large number into smaller numbers so that you can get the least residue. But then with Fermat's theorem, that is implementing the formula that he came up with. Now since it's the modulo of 7, so simply I can just write it as 18 to the power of 7 minus 1 is congruent to 1 mod 7, which is then 18 power 6 is congruent to 1 mod 7. Now 18 power 18 can now be written as a factor or multiple of 18 power 6. It's such that 18 power 18 is congruent to 18 power 6 into brackets to the power of 3, which then means which is then congruent to 1 power 3, because 18 power 6 is congruent to 1 modulo 7. Then 1 power 3 is just 1, so then all this is congruent to 1 modulo 7. Hence 1 is the least residue of.
I'm going to take you through the check dingits. Check dingits is a form of redundancy check used for error detection. It normally checks for mistyped dingits. There are two types of barcodes: the universal product code, which is a system numbering code used on products, and the international standard book number, which is a system used for numbering books. Here we normally check the last dingit to check for the ISBN, and the dingits here are positioned from right to left. Let's consider an example here where we have this particular number, and here we write our A10 all down to our left side, which is A1, and we write our number. Here when we are trying to calculate the ISBN, then we multiply the numbers: 10 by 0, which is 0, 9 by 4, which is 36, 8 by 1, which is 8, 7 by 2, all the way until 1 by 0, which is 0. After calculating, here we weigh the sum, which we divide the numbers by modulus of 11, 36. Our remainder is 3, 8, 8, 14, we have 3, 36, we have 3 all the way to where we have 0 and 0. We calculate the total, which is the sum of the numbers, whereby we get 22. 22 the modulus by 11, and 22, since it's divisible by 11, the modulus is 0. In ISBN, when the remainder is 0, then the digits given is correct. But when the remainder is other number apart from 0, then it's an invalid dingit. Therefore here our number is after we have checked the dingit called, the ISBN is correct. Therefore it's congruent and it satisfies the ISBN. Thank you.
Multiplicative inverses are used in modular arithmetic to find the division of modular arithmetic. In modular arithmetic, you cannot divide the modular arithmetic normally like you do in other normal equation. Like for example, dividing this equation by 4, it will give you 5 and 2 modulo 6, but 5 will not be congruent to modulo 6. So for that, we first take a look on how we do the normal division. In normal division, we divide a number by simply, the normal division is simply multiplying by the number you are dividing by 8, the reciprocal of that number. For instance, if you are dividing 4 by 4, you just simply multiply by the reciprocal of the number you are dividing in, like 4 by 1 over 4 is 1. But in modular arithmetic, we only use integers. Fractions are not allowed in modular arithmetic. So we need to find a number that will do the same work for reciprocals, and that the number we call the multiplicative inverses modulo n. So when you have this equation, AB congruent 1 modulo n, B is the multiplicative inverse of A modulo n. The least residue has to be 1 in this equation. For instance, 2 times 5 congruent 1 modulo n. In this case, 5 is the multiplicative inverse of A modulo 9. When it comes to modular arithmetic, we have two methods for finding the multiplicative inverse. When n is less than or equals to 13, we use the manual method. But with large numbers larger than 13, we follow the Euclid's algorithm first to find the highest common factor, and then with that formula to find the multiplicative inverse. For instance, in this example, we have A at n. N is equals to 13, so you'll use the manual way to find the multiplicative inverse. First, before you to know that A at n have a multiplicative inverse, A at n must be coprime. That is, they have only one highest common factor, which should be 1. Now 5 and 13 are coprime because they have only 1 as their HCF. So you first start by multiplying by finding the multiples of 5, starting from 1, 2, 3 up to 12. So like in this case, with A being 5, you need to find a number B that B multiplied by A will give another number A that will give a least residue of 1 modulo 13. So you start running by 1, which will give you 5 by 2, 3, until you get a number that will give A, which is in this case 40, and a least residue of 1 to satisfy the equation AB congruent 1 modulo 13. So in this case, 8 will be the multiplicative inverse of A, which is 5 modulo 13. The second method, you need to follow Euclid's algorithm to first verify whether A and n are coprimes. That is, Euclid's algorithm is used to find the HCF of those two numbers, where the first number, the largest number, becomes on the left side on the equal sign, and the smaller number is on the right side of the equation, on the equal sign. You find a factor that multiplied by n, and will give a remainder to find Euclid's algorithm to find the HCF. You have to repeat the equation by bringing 30 on the left side and 13 on this position. You repeat the steps until you find the remainder is 0. The last remainder in the second last equation is the HCF of those A and n. If the remainder is 1, then A and n are coprime, meaning they have a multiplicative inverse modulo n. But if the remainder is not 1, then there is no multiplicative inverse modulo n. So in this equation, the remainder is 1, so you can proceed to find the multiplicative inverse modulo n. So after Euclid's algorithm, you rearrange the equation such that the remainder becomes the subject of the formula and 73 goes to the right-hand side of the equation. So after rearranging the equation, they should be like this. The numbers are circled to mean that whenever this number is closer to another equation, it cannot be simplified. That is, any number circled cannot be simplified, but it should only remain as it is for simpler calculation. After rearranging the equation, you need to substitute the last equation going up once until to the first equation, such that in this case you start by substituting 4 with this equation, that is 13 minus 2 times 13. You repeat the same process after substituting 4. You substitute 13, and then you substitute, and after substitute 13, the equation is over. After substituting, as you can see here, you have to check if that equation is correct. That is 7 times 73 in bracket minus 17 times 30 will actually give you 1. If it was 1, we rearrange this equation so that after rearranging that equation, it will be A congruent, the least residue, modulo n, which in this case is 73. So that is, the equation has been arranged here. This 73 is the modulo equation. 1 is the least residue, that is should be 1, and that how it becomes. And in this case, after rearranging the equation, negative 17 becomes the modulo inverse. But if you take a closer look of this negative 17, it is not the least residue in that class. So you have to find the least residue using negative 17 as C and modulo 73. That gives you 56, which is the multiplicative inverse of A and N.
Now,
linear congruence is the process of proving that a value x is true in an equation given, like, let's say an equation like A, x A congruent to B modulo n. So we need to prove that x is true. So there are 3 ways of doing this. There is linear congruence with a solution, whereby the linear congruence, you find that A and N are cofactors, coprime, not cofactors. And then there is another method in which there are no solutions, that A and N have a cofactor in that they are not coprimes. And then there is the third method, which there are multiple solutions, in that you find that A and N have cofactors which is still divisible by the value of B. So if we start, find the value of x, we will multiply both sides of this equation, xa b by b, where b is the multiplicative inverse of A congruent n. Since VA congruent to 1 modulo n is 1, it follows that the solution of the linear congruence AX congruent B modulo n is given by x congruent BB modulo n. So let's use this example here, which I had already calculated. The equation is that 11x congruent 7 modulo n 8. We first find the value of b using the multiplicative inverse, in that AV congruent 1 modulo n. So in our equation, I found that my multiplicative inverse of 11 modulo n is 3. We can substitute the value of b in this equation. There will be x is equals to 21 modulo 8. 21 is greater than 8, so it will be. So 21 mod 8 is equals to 2 congruent 5 mod 8. So x is equals to x congruent 5 modulo 8. So that is the first method. Then when we proceed to further, we can check that for linear congruences without solution, let's use this example. 6x congruent 4 modulo n. You find that 6 and 15 are not coprimes, since they have a common factor, HCF, which is 3. 3 can divide 6 and can divide 15. So in this case, there is no solution. Then we proceed for the linear congruences with multiple solutions, which we will introduce a new integer d. Let d be the highest common factor of A and n, where n is greater than 1. So you see in a linear congruence equation, AX so the b modulo n has a solution if b is only divisible by d, which is the common factor of both A and n. So we can use an example of 9x congruent 21 modulo 24. We find that the HCF of 9 and 24 is 3. And still 3 is a divisor of 21. So when you divide that, you find that 3 divided by 9 becomes 3. 21 divided by 3 is 7, and 24 divided by 3 is 8. So after reaching here, you will find that 3 and 8 are copper primes since they don't have a cofactor. From here, we will proceed with our normal method of finding the multiplicative inverse of 3 modulo 8, and we solve this equation. Like you can see in this example here, I found my weight is negative 5. Substituted here to b, negative 5 times b, which is 2, b is 10. And then negative 10 modulo 8 is x congruent 6 modulo 8. So this x has a solution congruent 6 modulo 8. Thank you.
Shoot.
I'm here to take you through Affine Cipher. So Affine Cipher is used to encrypt messages. So before you encrypt a message, you are required to convert it to its equivalent letters. So as we know, A is allocated 0, B 1, up to Z is allocated number 25. So for example, if we have a message Ulabalo, which H in this case is number 7, L number 20, L still bado number 20. So we have been given an equation, EX is congruency to 5x plus 23 mod 26. So here in this equation we will substitute the value of the letters. So for our message we have 7 here. So we'll take the first number 7. So we'll look for E of x of 7, and then we compute this, and then we get, after computing, we get the value of E of x of 7 is 6 mod 26. Then we proceed for the value of 20, the value of 11, the value of 1, the value of 14, and the value of 0 as equivalent to what we have for our message. So after encrypting this message, we find that the encryption message becomes 6 19 0 0 2 3 2 23 0 15 15. So generally the equation for affine cipher encryption is EX A X plus B mod 26.
Shoot.
So after encrypting the affine cipher, we can perform decryption for the message that we had encrypted. So for example, if we have a message 22 8 11 22 and 9, and then we have been given an equation that was used to decrypt this message, which is E of x is congruent to negative 9x plus 6 mod of 26. So we know generally from the equation to decipher, which takes the form of dy equals to v of y minus 6 from this equation, y minus 6 mod of 26. So step 1, we find the multiplicative inverse of negative 9 is negative 9 modulo 26. So we take negative 9 and modulo 26, and then we find the multiplicative inverse of them. So after simple calculation of where we take that x multiplied by negative 9 is congruent to 1 modulo 26, so we get the value of x to be negative 3. So we take the equation E of x equals to negative 3, so we replace negative 3 to this equation to d of y, v y minus 6 mod 26. So we replace with negative 3 y minus 6 mod 26. So we do as what we did for encryption. So we take the first value 22, so we take E of 22 negative 3 into 22 minus 6 mod of 26. So we get negative 48 mod of 26, which is equivalent to 4 mod of 26. So next we proceed to E of 8. So negative 3 8 minus 6 mod of 26, which is equivalent to negative 6 mod of 26, which is equivalent to 20 mod of 26. So next we proceed to that of 11, and then we do for that of 9. So after decryption, we find that from the letters that we allocated from the numbers that we allocated to every letter, we find that E is allocated 4, U is allocated 20, L is allocated 11, 4 is allocated E still, and then 17 is for R. So after decrypting this message, we find that the message becomes Euler.